This math help video is on partial derivatives. I recognize that many of you haven't seen partial derivatives before, but the good news is we draw the techniques for doing partial derivatives directly from the derivatives you're more familiar with. In many cases, we have to deal with functions that vary with more than one independent variable. For instance, if we have a function v that varies with both position and time, such that v equals x plus t, keep it very simple. If we draw a graph where time t is the horizontal axis and the vertical axis is v, then we can graph the function v, but we have to pick an x. So at x equals 0, then, and at t equals 0, we start at the origin. And we just draw that like that. And we'll label this. This is v at x equals 0. If we moved positions to say x equals 1, then at time equals 0, v equals 1. It would have the same slope with respect to time. It would just start with a larger offset. So this new curve, it's parallel, and it's v at x equals 1. And we could keep doing that. You could draw another one in. That would be v at x equals 2. Now, all of these three lines are parallel. They have the same derivative with respect to time. We can still do the rise, delta v, over the run, delta t. And on any of those curves, it'll be the same. And that's the slope, right? So m equals delta v over delta t. We also know that's the derivative, but we have to be a little more specific here. We could write it as dv dt equals, it's going to be the slope m delta v over delta t. But in this case, we have to evaluate this whole function. And this can get tricky. So for right now, what I'm going to do is I'm erasing the x, and I'll replace it with 0. So that's that first curve that we're looking at here. And now this derivative becomes easy. It's what we've done before. So dv dt is just the derivative of t, which is 1. I can replace that 0 now with a different constant. Let's take x equals 1. dv dt is still 1 because the derivative of 1 is 0 plus the derivative of t, which is 1. And I can keep doing that for any value of x. It doesn't matter. So dv dt is still 1. Because what happens is, when you take a partial derivative, you hold the other variables constant. That's the only way you can do it. That's the rules for partial derivatives. So we have to be along a curve where only one variable is, and that's the variable you care about for the derivative at that moment. So here, dv dt is 1. I can look at dv dx too. And it's just like looking at the dv dt. For dv dx, we have to hold time equals constant. So we pick some time t here, whether it be time equals 0, time equals 1, time equals 10. And when we do that, I think you can see that we're also going to get the derivative equal 1. So dv dx equals 1. So we're playing by the same rules. In the first case, we took dv dt and we held x constant. In the second case, we took dv dx and we held t constant. That's following the rules of partial derivatives. It's often written dv dt equals 1 in this case, and dv dx equals 1 in the other case. The change was this curly d, and that denotes a partial derivative. What it implies is we're taking the derivative with respect to the variable below, in this case time, and holding the other variables constant while we, in this case x. That's really everything you need to know for calculating partial derivatives.